you how it is used in various medicinal chemistry, that is to cure various types of stuff. And then I will talk about lithography, which is a very powerful technique. It is used in various types of industry, starting from printing, just regular paper printing, to making circuit boards for computers, and also making the diagnostic tools for medical applications. And also talking a bit about basic surgery. All of these things, they are used every day today, and they all involve very simple chemistry, no complex things. The only thing is like 2 plus 2 cycloaddition, or cis-trans isomerization, or single oxygen oxidation, or just breaking a bond, converting it into carbon dioxide and water. Okay? So I will talk a little bit about the use of photochemistry in synthesis. You know, the chemistry, quite significant part of chemistry is about making new molecules. New molecules, mostly organic, which is there's a lot of people who do organic synthesis. Synthesis of compounds which are used as regular medicines or to make some the monomers for industrial products like nylon and all this sort of stuff. In some of the photochemistry is not that much used in industry to make molecules, because to use photochemistry you have to have huge plants which wear lighting, you have to shine lights and all of these things, and oftentimes there is a perception among the industrial synthetic chemists, photochemistry gives mixture of products. So if you really want some simple synthesis, it has to give a clean one product, not some 25 different products, and then you get 10% of this, isolate this, separate, preparation, they don't know about this. Okay? So still, photochemistry is used in synthesis when they cannot find any other methods that is as simple as this, otherwise they will go for this. Okay? Today, the most popular approach, synthetic methodology, is what is called as visible light photocatalysis, where you use the sunlight to make the molecules, but in a catalytic fashion, which is very popular. Okay, I'll tell you a few examples, not that many. Rose oxide, as the name suggests, rose oxide is a perfume. Perfume, you don't need a lot of it, you need tiny amount. You spray on yourself, you smell very good. But if you want to have a drug, you will have to make a lot of it. Okay? And another thing is vitamin D. Vitamin D is essential. If you don't have vitamin D in your body, the bones will disintegrate. That means you cannot stand. Okay? If you look at the old people, some of them, they have problems with their bones. They have the bones, if it breaks, it will take a long time to heal. And caprolactam, this is used, for example, in nylon. Making nylon, most of us wear some clothes which is made up of nylon, rayon, decathlon, all these kind of polymers which are considered to replace cotton with all these polymeric materials. You need a monomer. That monomer, nowadays I think China makes the most amount of nylon. Once upon a time, nylon was invented by DuPont. After about 20 years, they just sold everything. They realized it's not a very profitable business. So we are making large quantities. Okay? I will talk a little bit of this and then I will move on to something else. Okay, rose oxide. Rose and then oxide. So we can see here, rose oxide, again, if you have taken some organic chemistry, you should know this compound is chiral. That means there is a carbon center which is 4 different groups. If you have 4 different groups, the molecule can be optically active. That means you can have a mirror image, like a left hand and a right hand. Left hand and right hand, they are not the same. You cannot overlap them. You can overlap like this, but this is the way you should overlap. But then you can see this finger is on this side and finger is on this side. That is. But if they have opposite they have mirror images, they have different properties. So if you want to make a medicine, you have to make only one isomer. You cannot make two. If you make both, one can be good, another one can be pretty bad. So sometimes it can cause serious side effects. Okay. So here, rose oxide, you can see here R and S. This is S and R. So these two are mirror images. If you put on top this one on top of this, it will not overlap. Okay. This is, if you are taking into organic chemistry, this is the basics of organic chemistry. You will read a chapter on stereochemistry. They will talk over and over about this. Okay. So between the rows, it produces only one of these two compounds. It doesn't produce both. If you go to the market, buy rose, you smell, it's very pleasant. But you cannot have a lot of roses and crush it and then take a bath with a rose paste. It's going to become very expensive. Okay. So you have to make these things cheap and then also make a lot of money. So this is good with the companies in Switzerland. Hoffmann La Roche, they are very good with CBA. They make this kind of compounds. They make enormous amount of money. Switzerland is a small country. They cannot afford to make tons of iron. But if they can make something simple and small amount and make a lot of money, that's what they want to make. Right? So they make this. An example here. This is one isomer, this is a different isomer. So you can see this is 0.5 parts per billion, and that will still go to 0.5. And for this isomer, it is 50 billion. There is about 500 times more of this. If you take 1 ml of this and put it, this one, you got to take 500 ml of this, and then all over the place you got to spend the same amount. Okay. So the way to make this compound is very simple. There is no other escape without using photochemistry. You remember this compound? Okay. We talked about this compound in this board here. Do you remember that compound? You should remember. If you don't remember this compound, then you should take some tablet to improve your memory. This is single oxygen. Okay. So ground state oxygen. And then if you excite it, you will produce single oxygen. That single oxygen, I already mentioned it to you, is very reactive. So that is what we use for curing cancer. Okay. So that single oxygen can also react with the molecules like this, and then it will produce this kind of peroxide. This is a very simple reaction. So take the olefin and bubble with single oxygen, and then you get a compound. And this compound, as you see here, the double bond has been shifted to this, and then you have made this alcohol. Okay. That is a simple reaction, no big deal. Okay. Now the same reaction, if you have the right starting material, you can make the rose oxide. Then you make millions of dollars. That's what they do. So this company, they started with this citronal. This is the one that you have a lemon. When you have a crushed lemon and smell it, you will have this lemony smell or taste. That is, this one is very cheap. You take the compound, react with single oxygen, you get go through this peroxide, you get this one. This is a simple chemistry, no big deal. So you start from this, you take a lemon from the backyard, react with single oxygen, you get the rose oxide. The lemon is very cheap. Rose oxide is like 10,000 times more expensive than this lemon. Okay? So you make this. This is how they make the Hoffmann La Roche makes the rose oxides. They have a patent on this. When they have a patent, you cannot take it. Okay. So if you use this procedure, they will take you to court. So, but now the patent has run out about 20 years ago. So once the patent runs out, anybody can make it. So anybody can make some money by making this compound. In the older, see, this is a plant, and this is the rose oxide, this is the rose granule, which is used to have sensitized single oxygen. You pump this citronal and irradiate this thing, out comes the rose oxide, and then this other stuff. since the patent has come out, everybody can mix it. So for example, take here, same compound, and these are all the things usually done like this. It is on the rooftop. At the end of the day, we have rose oxides, put on and go home. You don't need to go and buy this stuff in the store. This is a very simple chemistry that is used for this purpose. Okay. So originally the synthesis of rose oxide was done by Hoffman. But that is a very basic, simple discovery. But they were able to make millions of dollars in about 20 years ago. Okay. Now they realized they moved to something else. They make vitamin D. Vitamin D is present in milk. If you if you drink milk, you have the free vitamin D, not vitamin D, but you will have vitamin D. But if you want to make vitamin D, you have to have a lot of sunlight, because the compound that goes into your stomach, it comes eventually to the skin, and the light comes when you walk in the sun, that will get converted into vitamin D. It will go back. That is what is keeping your bones strong. Okay. So what vitamin D what it does is, when you take calcium, it absorbs the calcium into the skin. So the vitamin D is absolutely, it is essential for attracting this calcium into your bone. If you don't have vitamin D, even if you take a lot of calcium, it will not go into the bone. Okay. So if you don't take vitamin D, what will happen is, for example, like this small boy, see all his bones grows all kinds of things. This is called, disease is called as rickets. So this is in countries where there is not enough sunlight or where there is no good milk. This is the problem. Okay. So in America, what they do is, when you buy milk, they will purposely add vitamin D into the milk. That is, you cannot buy milk without vitamin D. So when you drink milk, automatically vitamin D goes into your system. Okay. So in the older days, the vitamin D comes from, though you need vitamin D, and it comes from, for example, you start from dehydro. So in order to vitamin D, you have to take a lot of it. That means the material should be cheap. No, you cannot start from very expensive rose oxide and make vitamin D. That means you can take vitamin D once a month. Okay. So the vitamin D precursor comes from animal skins, cow, pig, and sheep. We all eat the pig and sheep and everything. Whatever is left, like hair, skin, they contain this compound. If you can convert this compound into vitamin D, it is very cheap. Because we are killing every day millions of these animals and then eating them, and then we throw the skin, we throw the hair and all this. From there we pick it up, convert that into this compound. So the way the chemistry works is also very simple. Many of this chemistry is not very complex. If you just study some 10 pages of organic chemistry, you can know all these reactions, how these people make money. Okay. So for example, this is the compound what is called as sterols, ergosterol, dihydrocholesterol. These are the ones present in animal skin or animal hair. Okay. You collect all this, extract it, and you expose it to the light. It becomes this compound. That is, this bond will break and it comes to this. Again, this reaction, if somebody in this room is an organic chemist, they would have known this reaction. This is a simple 6-electron heterocyclic ring motor. This is the one that reaction Woodward and Hoffman, they got the Nobel Prize for this discovery of these rules of these reactions. Okay? So when it opens up, you get this. Now, this one hydrogen will migrate from here to here, and when it does migrate, this one goes from here to here. At the end, you get vitamin D. Okay. So the key step is this one. So this compound comes to your skin, and then when you lie down in the sun, and then the sunlight, it goes to this. And last step is basically thermal reaction. You get this 1,7 hydrogen migration. These are all very basic organic reactions. and it works every time. These are all 100% reactions. Okay. So as you see, H mu means light. So this compound goes to this compound, and this is in countries like Scandinavian countries. There is no sunlight. Sometimes there is no. The days are like 20 hours a day. Long days. Night will be very short. So you go to bed around 12 o'clock. Still there is light. When you wake up at 4 o'clock in the morning, still it is very bright. Okay. Or the other way around is sometimes completely dark. So 12 o'clock is in the afternoon, it looks like midnight. Okay. So if you have no light, no vitamin D. Okay. So the company, when you make this, irradiate this, you get that compound, and this isomer for hydrogen to migrate from here to here, you should have a structure like this. This structure is, with respect to this double bond, is cis. You remember the cis and trans I mentioned in jaundice, same kind of thing. So when you produce it, you will get a mixture of this plus that. This one is unfortunately it is not useful. So you have to convert this back to that, and for that you use again photochemistry and do the cis trans isomerization. This trans will go back to cis and everything will go to vitamin. So this overall chemistry involves simple cis trans isomerization, making vitamin D, which is essential for our good health. It is made using photochemistry. Okay, this one is ready. Nylon. Okay, nylon. You must know what is nylon. I think some of you are wearing the jacket. Your jacket, for example, is made out of nylon. And the nylon is, when you go to the market, you buy nylon rope or nylon bag or nylon, the computer cover. Everything is made out of nylon. Okay. To make the nylon, you made this compound. This is a caprolactam. This is the monomer. That monomer gets converted into nylon, and depending upon how much is the cyclic structure, whether it is 6 or 8 or 10, you can make. So you want to have a cheap starting material. If you go to the market, how much nylon material is there, to make, if it is too expensive, nobody will buy. And nobody will buy. You cannot make nylon very cheap. Your starting material is very expensive. So you start from cyclohexane, and that react to the nitrosyl chloride, and then you make the caprolactam, and this one is polymerized to this one. So this reaction, which makes the monomer, which is the beginning, it has to be cheap. It cannot be a very complex process. So they take cyclohexane and then the light, and then make this thing. This is how it is made in Japan. Japanese industries, they make this monomer because you have to buy the monomer. You may know how to make nylon, but without the monomer, you cannot make nylon. Somebody is going to sell this. Whoever is selling this is the guy who is making money, not this guy. This guy has a market is much smaller than this guy. Okay. So again, the chemistry is useful. Photochemistry is useful. Okay. So it's the same technique is used over and over. For example, if you want to make a different type of nylon, this nylon, this size makes a difference with respect to how much it can stretch. If it is small, you cannot stretch it. If it is a longer chain, then you can get stretch it to small thing and keep it inside, and then it can become large. That's why it is important. Okay. So we all think that we think that we are smart, and we know how to use the light. Now we figured out sun is the source of light. Now if you depend upon sun, if there's a rainy day, then you cannot survive. So we somehow understood how to use the light to make things work for us. So, but even before us, the plants, they use light very effectively. The plants have been here even before us. Before you were born, there were trees on the campus. You are not the guys who put the trees. So the trees have been growing, but they grow just looking for light. So in many of the basic reactions, the plants use for survival are very simple. And without light, the plants will die. If the plants die, you will die. If there are no light, no plants on the campus or in China, and there will be no life. Okay, because the plants are the zero level life on the earth. Okay. So I will show you a few things. See, how does the plants grow? What is when to flower? Every year in June, July, you see the flowers coming out. Next year also June, July. We have a calendar, computer, it tells us when is June, when is March. But how does the plant know when is March, when is June, when is February, like that? So they have a way of keeping track of all this stuff. They keep track of these things using sunlight. Okay. And also, for example, the plants grow. When they grow only in the daytime. The night time they don't grow. Okay. That is because they look at the sun. Whenever the sun is there, they grow up a little bit. And the other thing, for example, the phototropism. When you put the plants know to survive, they need the sunlight. If you put the plant in this middle of the room, the sunlight is over there, they know. So there's no point in, they will not grow this side, they will grow towards that side. So somehow or other they are able to sense the light is on that side and they keep growing towards the window. But they are not growing towards this other side of the office. Okay? So they use again a simple chemistry using light to trigger this plant to grow towards that side. And for example, the most important thing is photosynthesis. Every day the plant grows. They are not going to the supermarket and buying something to eat. They just take water and take carbon dioxide and sunlight, and they make something, they grow every day. And after they grow big, you cut and you eat the plant. Or the other animals come and eat the plant. The important thing is the photo part is the most important. Without the photo, they cannot do synthesis. Without the photo, the plant cannot go that towards the window. And without the photo, they don't know. If completely there is no sunlight for a whole year, the plant will become completely confused. When to flower, when to give birth to the next seed and all this stuff. So they somehow have figured out all this stuff based on light. Okay, I'll tell you some. But this is a big area. This is very complex because it's not that easy to fully understand what is happening in all of these things. The other important thing is you are seeing me, I am seeing you. The vision. Without light, I cannot see. So if you turn off all the lights, if I am so much smart, I should be able to see all of you, but I cannot see. And I'm sure you cannot see me either, because there is no light. So the light is the main thing that is able to make us able to see things. So the light is the one which is triggering some action in my eye, which is telling the brain there is a guy sitting in front of you and he is looking at the computer, he is not listening to you, or he is looking at cell phones. That's how I am able to figure it out. Okay. So all of these things uses light and simple reactions, which is very amazing how the plants and animals and all these things, they have figured, not that they figured it out, it is somehow or other that got inscribed into the genes. Okay, here is the plant. Okay, the plant is growing inside somewhere, and then June, July comes, there is a flower. You didn't do anything to the plant. Nobody did anything to the plant, but then if you are waiting, you buy a plant, and you are very, very uneasy. Nothing is happening to the plant. I don't see any flower, nothing. I wasted my money. But then you see in June or July, it has a flower, because the plant knows that is the time I am supposed to flower. Okay. So what do they do is they use a simple reaction. These are called as phytochromes. Phytochromes are these kind of molecules. Yes. If you look at this molecule, it's somewhat similar to the jaundice problem. Okay. So here, you see here, there is a double bond, and then there is a double bond, there is a double bond. Okay. So when the light hits this molecule, this double bond will isomerize. So this molecule and that molecule, they have different absorption spectra. Okay. So what will happen is this plant will keep using this reaction going from here to here, coming from here back to here, to keep track of the time of the day. Okay. So how they do this stuff is, for example, you see here. If for us, well, it's not very obvious. The beginning, in the mid-afternoon, it's very bright. The evening, it gets a little bit, the light is slightly softer because it is the intensity is in a different region. Okay, and depending upon the month, you see the sun sets at a different time. So sometimes it sets around 6 o'clock in the winter, and maybe in the summer, maybe 8 o'clock in the night. Okay, so the intensity of the light and the wavelength shifts with respect to the day, or the time of the year. Okay. So what happens is there are two types of light: red light and far red light. So the plant, this compound, that is, this molecule will isomerize with one type of light, and that molecule will isomerize, go back to this one with a different type of light, because they absorb in a different region. So during the daytime, this molecule will go here. During the night, in evening time, that will come back here. So the plant will know how much of this one goes this way, how much of it comes that way. From that they can tell how much light is, that wavelength of light is present on each day. From that, at the end of about 3 months, they know that, okay, now I had about, these many long days, these many short days. That means the time is now, it is not June, it's probably April or May or something. So, and then the flowers will start coming out. The body will start functioning differently, and that's what happens here. See that? So you can see the slight difference in the light makes a difference. That's quite wrong. So if you go back, if you watch when the sun sets in April versus in September, they are not the same time. Every day, nowadays the computer will tell you what time the sun is setting. But the plant knows just by looking at the light intensity, they know when the sun is setting, and that's how they keep track of the day and the night. And at the end of it, the leaves and all this stuff, and now it knows when the leaves should come out, when the flowers should come out. Okay, this is a very simple chemistry. If there is no light, there is no flower. Okay, and the other thing is, for example, this is what is called. This is also simple molecule. They are not very complicated chemistry, because the plants they don't have any reagents to mix some 10 different things to make it complicated chemical reactions. This molecule has a double bond. If the light hits, it will go from here to here. Cis, this is the trans, this becomes a cis. And then it's connected to a big protein and all this stuff, and what happens is, when the shape changes, it will trigger the protein to do something else. Because eventually the proteins are the ones it's going to do, but proteins need to be triggered by something, what to do. Okay? So as you can see here, in the dark, the plant, I don't know whether you have seen, some plants when you walk by, the daytime it will be leaves will be like this, the night time they will close. How does the plant know when it is night or a day? Okay? So obviously there is some molecule which is going from one to the other. When it goes to the other, it triggers the protein, something else, and this protein, now you can see this is closed, the whole thing will close. And then in the morning this will absorb the light, goes back up, then it comes back like this. So it is, the plants, they do these things in a very simple way. It is very interesting. But again, to fully understand this, you need to do a lot more research, because this is basically, the basic part is the light. The rest of it is a little bit more complicated. So this is another one. For example, you keep this plant here. Okay, the plant may know day and night. The plant may know when to close, when to open, But more important thing is the plant has to know where is the light. If you keep the plant on the other side, if the sun is shining there is no point. Plant cannot walk from here to this place. Only way it can do is somehow or the other they bend and then see the sun. So, even when you get older, even for us to bend is difficult. But the plant, they can bend because they use the light to, if the plant is growing like this, it will turn around like this. And just because this part of it absorbs the light, and then you know the chemical reactions that triggers the plant to grow in a different direction. Okay, so this is for example, this is a little more complicated electron transfer chemistry, which is why doing this is called as cytochromes. The other one is called as phytochromes. These are called as cytochromes. As you can see, this plant, somebody kept it here, but you can see it is going towards the sunlight. Okay. So the plants can do a lot of different things. A lot more things. The plant uses light very effectively for survival. So the flowering to making life, the food for themselves, and all this rest of the stuff. Okay, one other thing I want to just quickly mention is vision. Your eyes is very important. Your eyes are the one which is to see things. Without eyes, I don't know what you think is the most important is your eye. Whether just you have the retinol and then all the rest of the stuff. Your eye, the main part is called as retinol, right? So the retina, if it goes away, then you cannot see. Some people have this problem of retina detachment. That means if a layer came out, that layer contains the most important thing for you to see. You can have everything else. It is like a car. You can have a nice car, seat, everything, but the engine is gone. The car is not moving. Okay, so if the retina is gone, you are not going to see. Okay, well, what happens is there is a molecule called retinol. Okay, that's why it's called retinol. Okay, that molecule I'll show you. It is a simple molecule, simple chemistry. Okay, this is the molecule which is called as retinol. It binds the protein. It forms what is called as rhodopsin. The eye contains millions of rhodopsins, tiny things in your eye. That is what absorbs the light. Okay, the rhodopsin, and when the light hits your eye, this, if you notice here, 1, 2, 3, 4 double bonds are there. This is the only one which is cis. This will go from cis to trans. And this is what is triggering your ability to see things. So this 11 cis isomer will go to all trans isomer. As it goes to the all trans, this protein will be released and that will trigger the brain. There is something in front of you. And then since there are billions of these rhodopsins, it can make a shape out of you, and that's how you see the picture. Okay. So the chemistry is very simple. It is again cis to trans, and it requires light. Without light, you cannot see. Okay. This is called again these are called retinol. This retinol, this is a different type. This is the same one, excepting this is all trans. And the bacteria, they use this chemistry to make energy. Bacteria rhodopsin, tiny, you cannot even see with your eye. They use this technique. When they see light, they produce a proton pump from which they can move. Otherwise, they cannot move. Okay. So from the retinol that you get to make your eyes, you need to make every day a lot of retinols. So the retinol comes from carrot, that's why carrot is called carotene is the main compound. Carotene is this compound. If you break in the middle, then you get 2 retinols. So if this one goes away, if you oxidize this, you will get the aldehyde, another aldehyde, then you will get 2 retinols.
That's why it's very important for you to eat carrot every day. You have to use carrot and tomato. If you don't eat those things, you will be deficient in retinol, and eventually one may become blind. So I don't know whether you eat a lot of carrot. I don't know whether in Chinese food you put a lot of carrots. No? You don't eat a lot of carrot? Carrot, what is the Chinese? Carrot, they should know, right?
There should be.
Yeah, there's a picture here. Yeah. So do you eat carrot or no?
I think yes, because I have seen in the supermarket a lot of carrots.
Okay, so because you need to have a lot of carrots to be able to keep your vision doesn't fall down with respect to age. Okay. So the original people who recognized this retinol is the most important thing for the vision is George Wald and these two doctors. George Wald is a professor of chemistry at Harvard, and they recognized why retinol, how does it function in the ability to see things. Also very important, when somebody appears in front of me, I cannot take 5 minutes to realize somebody is sitting in front of me. It has to happen immediately. If somebody comes in, within a matter of a few nanoseconds, I should be able to know that there is a person. So these reactions go extremely fast. There is cystotrans isomerization. There has been a lot of studies on this and a time scale of nanoseconds, picoseconds like this. And these people, they got a Nobel Prize in 1967, okay, about 50 years ago. Okay. Now, the other most important thing is photosynthesis. Do you know what is photosynthesis? Have you heard of this photosynthesis? Well, here is a huge tree, okay? And the tree every day they have more and more leaves, okay? Because they use the leaves to survive. They are not making these leaves for the animals to eat. They just want to survive. So what happens is, this process by which they synthesize something that is very useful for themselves and for others, that process is called photosynthesis. Okay. The photosynthesis was originally recognized. This has been in existence since the life on Earth. It is not some 1,000 years, 2,000 years story. This must have been there for hundreds of thousands of years. Okay. So Priestley is an American chemist who realized the photosynthesis, the basic things the plants use are carbon dioxide and water. Okay. They use only carbon dioxide. Now, when you go to a synthetic chemistry laboratory, you will see racks full of reagents. There are all kinds of chemicals to make some simple compound. But plants, they don't use all this complex chemistry. They have only get free carbon dioxide from the air and free water from the ground. They take both. They make sugar and everything else. The leaves. And those leaves contains a lot of things that we can eat. Okay. But by ourselves, we cannot take carbon dioxide and water and make all the stuff. You cannot drink a lot of water and carbon dioxide cylinder and take a little bit of carbon dioxide. You are not going to survive. Okay. But the plants can survive. Somehow they are able to make all this stuff. That process was originally recognized by him, carbon dioxide and oxygen. And also, the more important thing is they take the carbon dioxide, which we don't want. Okay. They take water, but if they don't take water, we will be happy, but they need the water. In the process, they release oxygen. If they don't release oxygen, we will die also, because we need oxygen for survival. So that's why it's very important to have a lot of plants around. If you cut all the plants, then there is going to be shortage of food, shortage of oxygen, shortage of other things, and then things are not going to be good. So he published a paper in 1774, and this is the beginning of importance of carbon dioxide and water. Okay, and for example, 6 molecules of carbon dioxide, 6 molecules of water, plus light energy, which is good for us for photochemistry, Otherwise, photochemistry, we don't have anything to tell how great photochemistry is. And it makes this. This was recognized by this guy Benjamin Franklin. Franklin is a very famous American politician, and he knew from Priestley that this process is most important, and then that's how the research on photosynthesis started. Okay, why photosynthesis is very important? First of all, plants know the secret how to use the solar energy and make food. Today, that's what we want to do. We want to use the sunlight and we want to make energy. Okay, we have the energy from petroleum, gasoline, coal, nuclear, all this stuff. But above our head, there is a sun. But all the plants sitting around, they know how to convert the sunlight into something else. But we have no idea how to do that. So that's why it's very important to know. So the plants provides energy for the sunlight, produces energy for the plants. The plants provide energy for animals, and then small animals like all these things, they eventually provide the energy for most ecosystems on Earth. So if there is no plants, at the end of it, the sun is there is no survival. Everybody will go away. Okay. So this was recognized. It is not new. 100 years ago, this guy, he's a famous photochemist. He realized if you can convert sunlight into something else, more useful energy, then you don't have to depend upon oil or gasoline or any of these things for electricity, for making more energy. Because we need energy. Without energy, you cannot run this projector, or there is no light in the building, or if you go to the supermarket, there is no food. So energy is absolutely essential. For that, if you can figure it out, how to convert the sunlight into any other energy, that is the big deal. So he said in 1912, this is what is going to happen immediately. 1912 today, almost 100 years, this is what happened. Because we still are not able to figure out how the plants are able to convert solar energy into something more useful than chemical energy. We are trying to understand the process, and there's a lot of money goes into understanding this chemistry. Okay. So the original this chemistry, little bit understanding was done by Kelvin, for which he got a Nobel Prize in 1961. Okay. And then the understanding the structure of these proteins are involved in the plant. Okay. So these three people, they saw the structure. They saw the structure for this crystal structure of this enzyme, which is absorbing the sunlight and doing something which is playing a critical role in the conversion, and this for which these three people got the Nobel Prize in 1988. Several people got the Nobel Prize, but still the process is not well understood. Okay, basically, Kelvin, these people, and recently Marcus, again he got a Nobel Prize, so a lot of Nobel Prize, but still the chemistry is not fully understood how to use the sunlight to make energy. Okay. Okay. I don't know whether you realize your future depends upon finding a new source of energy. Okay. The energy supply for everything that you do, starting playing with your computer to watching TV or going home in a car, all of these things requires energy. The energy today comes from, for example, in 1973, it came about 40%, 50% of it came from oil, that is the gasoline. Okay. And then today, it is about 30%, 33%, it came in 2009. In 2019, it is about 25% of it coming from oil. Because the number is decreasing from here to here, because the oil supply is, we have, the more and more oil we take out of this, the well, there is less and less of it, there is no oil. So By the time you become a grandmother or a grandfather, there may not be any oil anywhere in the world. So that means you cannot drive your car, you cannot drive your turn on your computer, all this stuff. Okay? So it is very important to find a new source of energy. The new source of energy is above your head, which is the sunlight. So you have to figure out how to convert the sunlight into something more useful. So here, for example, the other things are the natural gas, and then biofuels, coal plant, all this stuff. Okay, all of these things are natural sources. They will go away. After the time, maybe 50 years, 100 years, they're all gone. Then there will be a big war between various countries for all this kind of stuff. Okay. So now what we are trying to do is all the oils. It is not that somebody poured all the oil into these the deserts in Middle East. Okay. All the plants, when they die, eventually they become an oil. The plants to become an oil, it takes about 70 million years. It is not yesterday. 70 million years is long ago. Okay? So all those plants which died about 70 million years ago, they are the fossil fuel. They become the coal. They become the oil, and that's what we are using today. And there is enough supply only for about 500 years. In 500 years, you will have zero supply of coal, zero supply of petrol. Now, if you want to wait for again some more oil, everybody has to sit around for 70 million years to find it. So, in the meantime, the most important thing is figure out above our head there's the sun, which is producing a lot of energy. And the plants, they know how to convert that energy into some chemistry. So if we can understand the plant, then we can understand directly from sun to ourselves. We don't have to go through the plant. Okay? So that's what we call as solar energy. Solar means sun energy, we need energy. This is what, if you look around, every country, they spend enormous amount of money on figuring out how to produce solar energy. This is very common. They may be making vitamin D or rose oxide, all this. Okay, if you don't smell good, it's not a big deal. If your bone falls apart, it's okay. You can watch, you can walk with a stick. But now, if there is no food, what is the use of having a strong bone and then you spinning better? Okay, so you have to have energy. So solar energy that is using sunlight, we try to do this in different ways. Sunlight comes in the form of heat. It's very obvious. If you put a lot of water in the sun, it becomes hot. So that means you are catching that sunlight in the form of heat. But converting that heat into something useful is not that easy, because you have to have a whole lake of water getting hot. Okay. The other approach is converting sunlight directly into electricity. That is the easier approach, if you can do it. The other thing is converting sunlight into chemical energy. That's what plants do. They don't make electricity. They convert sunlight into chemistry, and that chemistry is the one that is used by all of us for survival. So today, a lot of research is done on these topics. Okay, sunlight is when you see the sunlight that comes down, it is in the region between 360 nanometers and about 960 nanometers. So if you are that's why the plant's leaves are green. There is no plant which is, if the plant already has died, it will become brown. The tree doesn't want the tree, so all the leaves fall down. The green leaves are the ones only sticking, because they know to absorb the sunlight, they need to have a green molecule in the leaves. Okay. So if you are going to do something with the sunlight, you have to use a molecule which is absorbing in this region. So a lot of time, a lot of research is spent on finding organic compounds or inorganic compounds which will very strongly absorb in this region. Once it absorbs, we should be able to tap that energy for something else. Okay. So there are two types of things which are called solar cells. Solar cell, probably you know what it is. See, sometimes you see on the house rooftops. Now all these things happened less than 20, 30 years ago. Before that, there was no rooftop with solar cells. But now there is more and more push for these things because the oil wells in Middle East or wherever it is, Russia and all those places, it's going down. You cannot pour oil into the well anymore because that well has to be filled with things. So basically what should happen is you have a silicon or dye-sensitized solar cells. So the molecule, if you have the right molecule, it will absorb the sunlight, it will go up, the electron will go up. So when the electron goes up, so that energy is stored in this cell, solar cell. When they recombine, electricity will be generated. That is ideal. Okay. So now there are lots of problems. It is not that straightforward. It looks very simple. Idea is very simple. Basically, you want to have a molecule, sun hits the molecule, the electron goes from here to here, and that much of energy is stored in the molecule. But that molecule, once the electron will come back down very quickly. It will come back down in nanoseconds. So if you are going to be successful, you have to catch the energy in that time scale, convert it to something else. Okay. And also this molecule, when it comes down, not everything you can convert down into energy. So the percentage of efficiency is going to be extremely small. That is why when you have in the houses and plants, you have these solar cells, they have lots of these things. They are not having one small big piece like this, like a leaf. You cannot spread a few leaves on top of your house and hope to have lights inside the house. So you have a whole racks full of this. The other thing is, as I already showed you, the spectrum, your molecule should be able to absorb as much of the solar light as possible. If it is absorbing only this much, that it is not using a lot of it. So if your molecule is going to more of it, it is better it is. So you have to find some organic compounds or inorganic compounds which will absorb the most of the sunlight spectrum. Okay. So there are two types of cells. One is called silicon solar cells. Another one is called as dye-sensitized solar cell. Drexel is a professor at Switzerland. They are very famous because this is one of the most important research topic in chemistry. Okay. And here what you do is you find various types of organic molecules and then coat on top of something, it will absorb all the light. Absorbing light is one thing. Converting this absorbed light into some useful energy is the second part. That is the most important part. Okay. Okay. Basically solar cells, what it is. Okay. The solar cell, again, this has been known for some time. Only recently people recognized it can be useful. The original research on this topic was done by, again, Albert Einstein was the first person to point out this can be done. That is the photoelectric effect, which is when you hit something, the light hits a molecule, the material, electron can be ejected, so that will result in electron separations, and when they come back, the energy will be released. And over a period of time, silicon solar cell, in 1980s, this became very popular. But silicon solar cell is expensive. It is not cheap because the silicon, getting a pure silicon is not that easy. Okay. So this is the region in which a solar cell, your sunlight is there, and then you have to find the right region. But when you use an inorganic material like a silicon, they absorb a single spectrum, not like organic compound. Organic compound, you will see an absorption spectrum, whereas the atomic or the atoms like silicon, any kind of thing, they will have a single line. That means absorption coefficients is going to be not very useful. That's why silicon solar cell, although that is the most popular one, China makes the most silicon solar cells compared to any other country. Even America tried to make it. Actually, their market is, China has overtaken that, so America has abandoned that technology. Okay, this is how it looks. Okay, so you can see all this stuff all over the place. Okay, you can see when you drive home, you may see these kind of things, or a rooftop of your house or the market, you will see some of these things. If you use these things, you don't have to use oil. So that's the goal. So this should be cheaper than the oil. If it is expensive, Nobody will use it. Now it is still expensive. Compared to oil, it is more expensive. So there is less and less use of it. But government is pushing people to use this thing. So they subsidize these things. Because in about 50 years, the oil price will go up and up and up. Now at that time, this will not be, nobody has used it, then this technology will disappear. Okay? So basically all these are silicon, they absorb the sunlight, and there is electron separation, and they come back, energy is released. Okay? Okay, so this is how it works. Okay, we don't need all this. The efficiency for this is 8 to 10%. That means it is not good. If you are a synthetic chemist, if you are making a compound, it is only 10% yield. It is not worth it. Okay? But here, 10% is still considered to be great because there is no other technology. If there is an alternate method, then 10% is bad. That's why everybody is looking for something, a better method than this silicon technology for this kind of stuff. So, for example, this is a American Chemical Engineering News for 2016. So they like to have, because the plants, they know the secret of how to convert sunlight into energy. So if somehow you can talk to the plant and figure out how they are doing it, then you can probably copy it. But it's not that easy. You cannot talk. Nobody can talk to the plant, and it is not going to tell you how they are doing it. So here is a leaf, supposedly with the artificial leaf. Basically, if you have something you plant outside with all the circuit boards, and if they can absorb the sunlight, and then you can make it, it's great. Okay. Okay. So far I told you something, a lot of stuff which are good about light. You can make rose oxide, vitamin D. You can make computer chips. You can cure a lot of disease. But that is not the end. Unfortunately, the light also is bad. Okay. So you have to figure out how to stop these bad aspects of light. It is not the bad, light is bad, but something that we do is bad that is making the light look bad. Okay. So this was invented by these three people. Molina, Roland was the most famous guy of these three. They showed many years ago, that is they got a Nobel Prize in 1995. In the world, there is something called ozone hole. You might have studied all these things in the newspaper. If your parents, they are scientists or engineers, they might have told you this is a problem. This is a problem for the world. This problem is created by us, okay, not by anybody else. So what happens is, the sunlight that comes from above, it contains UV and far UV light. If the UV light and far UV comes to your skin, you get skin cancer. So the cancer is going to, there is going to be widespread of cancer over a period of time. But if you look at here, in 1979, the sun, if above your head, if there is a screen which can cut down this UV light, that will not come down. So there has to be a screen. That screen is ozone. Ozone is present above your head. That ozone absorbs in blue. So all the UV light will be gone. So what you get is the good part of the light. I showed you this picture. You can go back to that. Okay, so the light that is coming down is completely from that end to that end. Some parts of the light that is here is not good. If it comes and your skin will absorb. If your skin absorbs, then it is eventually developed into cancer. Okay? So if you somehow can get rid of this light coming down, then you don't have to worry about that part. Normally, ozone that is already above your head, it will absorb that part. If you keep removing the ozone, more and more that the light in the UV region will come down. That is called as, So normally the ozone is produced under normal conditions and then it will happen and all this. So okay. So since the last 50 years, we use something called a freon. You know what is freon?
Yeah.
Freon.
Yeah.
When you spray something, something comes out. The bottle that you leave out, it contains freon. Or the refrigerator. When you want to cool something in the room, that contains a freon inside. That freon, when it is released, it goes up. When it goes up and reacts with the oxygen, it will react with the ozone, and the ozone will be converted into the oxygen. So more and more of this freon you release, more and more of ozone will be gone. Okay, this was not known some time ago. Again, DuPont was a company which invented freon. They had a big market share on this freon business. So if this is the chlorofluorohydrocarbon is the freon, they react with the ozone, and then eventually the ozone is gone, and then you end up with UV radiation. All the big cities, anything, end up completely, the light that comes down, it contains UV, and everybody will have problems. And this was what was pointed out by these people. In 1979, the ozone, as you can see, the blue tells you that is whole. That means that part of this ozone is gone. In 79, there was very little. In 2016, almost, this is above your head, the whole world, above the earth. And you can see that a big hole. When the light comes through this, it's going to be UV. Okay. So now, this chemistry, we'll go back. So this is called as, now people have realized this problem. This is the freon is the main problem for creating this ozone hole, and we have to stop it. The only way you can stop it is asking everybody not to use these kind of chemicals. And I can tell you not to use, but there's no guarantee you are not going to use. But the freon that you release here, it may end up on top of Russia, or it may end up in New Zealand, because it is going to go all over the world. So it doesn't matter who releases, whether it is India is releasing, or China, or America, or any country. So eventually the problem is for the whole world. So now there is something called as Kyoto Protocol that was done about 10-15 years ago. So you cannot use freon. So this that has been banned. So the freon that we use is modified version of the freon. I think almost all countries agreed on this, and eventually that will go away. Okay, so we are almost at the end of this. Okay, I want to tell you some few things. In life it is good to make money. And also if you cannot make money, if you are famous, you feel good about yourself. At the end of it, the goal is to feel good about ourselves. As a person who is rich, or who is famous, or who has done something good for everyone. Okay? So here are some people. This is the guy who invented lasers. This was done in 1960s. Okay? Some of these things are not that old. It may look like this has been here forever. He got the Nobel Prize in 1964. 64 is about 55 years ago. All right. 55, I am more than 55. Okay. So this guy, that was the time when he invented, and Charles Towns, who was a faculty at Columbia University, he was the first person to discover the ruby laser I showed you in one of the slides. So he got the prize. Okay, and then once laser spectroscopy came into picture, there are a lot of advances we were able to make in photochemistry and photophysics, because normal chemistry takes place very slow. It can be a few days, or it can be a few hours, or it can be a few minutes. But photochemistry takes place in picoseconds. That means 10 power minus 12 seconds, 10 power minus 15 seconds, like that. So if you want to follow these reactions, you have to have techniques. So the techniques requires time resolved spectroscopy. So many of these time resolved spectroscopies are very complex. Okay. The first one of these things was discovered by Narish and Porter. It was a microsecond time resolved spectroscopy for which they got a Nobel Prize. But today this is very routine. 1967 this was considered was a big discovery. Okay. And then in Ahmad Zuhail, I don't know whether you have heard of his name. He is a very famous chemical physics or chemist. He is about my age. Unfortunately, he died a few years ago. And he got the Nobel Prize in 1999 for the same technique, which is a flash photolysis, but it was done in 10 power minus 12 to 10 power minus 15 seconds. 10 power minus 15 seconds is extraordinarily fast. So to do anything in that time scale, to watch the molecules and all this, you need a new technique. That's what he discovered, and then that helped to understand many things in photochemistry. And this helped these people to become very famous. And they also, when you say Nobel Prize winner, everybody looks at him. When he walks into the room, you probably won't even listen to my talk. You will keep, everybody will be turning back and look at the guy. Okay. So that is the, and for example, this one is 2008. This is the GFP, green fluorescent protein. This is one of these person is Roger Shen. He's a Chinese, and he was at United States. So he showed that some of these animals in the fish type of stuff, this is jellyfish and all this under the sea, they fluoresce, they produce light. Okay. So by a chemical reaction, they produce light and all this. That is called as green fluorescent protein, and they got a Nobel Prize in 2018. These are considered to be major discoveries which helped advance the field. And these are lights that I showed you, light emitting diodes, LED, the green, the blue, the yellow lights that you see on the road. This was the discovery of these people. These are the three Japanese. This is the light LED. This is called LED. You will see, keep hearing LED, and they got the Nobel Prize in physics in 2014, about 5 years ago. So these are all not that old discoveries. So you are young. There's a lot of things that you could do. Maybe when I give the talk 5 years from now, I may be able to put one of your pictures there and say, okay, so and so did this thing, big deal, got the Nobel Prize. Okay, I think we are done. Eventually, so I talk about a few things where light plays important roles. If I keep saying light plays an important role, that is not enough. You have to know what exactly is light, what are the various things it can do to a molecule, and all that. We will talk tomorrow, day after, and all that stuff. Okay? I think we are done. Okay? So, all right. This is one of the Indian scriptures, written about 3,000 to 4,000 years before. They realized that the sun and the sunlight are the most important things in the universe. So you can see here, from the sun arise all beings, the sun sustains them all, into the sun they all vanish, what the sun is, what I am. So if the sun is not there, you are not there. Okay? I'm pretty sure there must be something like this in Chinese too. This is an Indian version where I know a little bit more about India than China. And I know a little bit more about America than I know about China. Okay, all right. So we'll see you tomorrow, 8:30 in the morning. Okay. Good. We are done for the day.